In the gym kit you just played, you reviewed some of these vocabulary words. Hopefully they're familiar to you, but if they're not, I'm going to teach you from zero here. Now we're going to start working in a unit about triangles. There is so many things we can know and talk about when it comes to triangles, so we're going to start at the beginning and how to classify them. So you're going to see this word a lot. It says classify. That means I'm trying to have you describe the triangle in some way. One of the ways we can describe the triangle is by its angle measures. So we're looking on the inside corners of the triangle. This first one right here is called a right triangle. Obviously, because you see the little box there, it means one of the angles measures 90 degrees. Check, done. You have this angle right here is our obtuse triangle, because that angle is an obtuse angle. It's bigger than 90 degrees. So if one of the angles is bigger than 90 degrees, it's called an obtuse triangle. So we have our right triangles, we have our obtuse triangles. If all of the angles are less than 90, it's called an acute triangle. So none of them are bigger than 90. They're all less than 90. And then you have a really specific one called an equiangular, let me try that word again. Equiangular triangle. Equa meaning same, angular meaning angles. So what do we think that means about all three of these angles? They're equal to each other, they're congruent. Remember, our symbol for congruent is an equal sign with a little tilde on top of it. We also know that they're congruent based on the arc marks. You see how this angle, and this angle all have one arc mark? We are indicating that they are all the same measurement. It's called equiangular. Those are the four ways you can classify a triangle by their angles. We can also change gears and classify triangles by their side lengths. If no sides are congruent, it's called a scalene triangle. Now I know that all three are different sizes for multiple reasons in this picture. One, they look different. And number two, so these triangles, again, like I said, we know that they're different angle or different side lengths. One, because it straight up looks like they have different side lengths. But what do you notice is not on any of the sides of this triangle that I gave you here? No red lines. We have no tick marks to indicate that anything is congruent. So if you don't have any tick marks, you're going to call it scalene because it's indicating that none of the side lengths are the same because there are no tick marks. On the other hand, if you have two side lengths that are the same because of these tick marks, so we have this side length and this side length being the same or congruent, then it's called an isosceles triangle. I don't know why, but it always stuck in my head that the word isosceles kind of looks like ice cream cone. And an ice cream cone, if it was a triangle, has two equal sides and one that's not the same. That's how I've always remembered it. I don't know if that makes sense to you or not, but isosceles looks like ice cream cone. That, if I turned it sideways, looks like an ice cream cone to me. The last one is called equilateral triangle. Equa meaning same, lateral meaning side, so it's equal sides. Again, I also noticed that these have all of those tick marks that indicate that all three sides are the same. So an equilateral triangle has three congruent sides. Again, congruent meaning they're equal to each other in length, so equal with the tilde on top. Okay, so again, that's kind of what you did in your gym kit, but here's the notes just again in case you've forgotten. Let's work on classifying these triangles by angles and by sides. So looking at the side lengths of number one, is it scalene, isosceles, or equilateral? I heard somebody whisper it. What is it? Scalene, because they're all three different. I have one tick mark, then two tick marks, then three tick marks, indicating they're all different. This is called a scalene triangle. But if we classify it by its angles, we would either use the word right, obtuse, acute, or equiangular. What should we use for this one? Obtuse. How did we know it was obtuse? That's correct. Yeah, this angle right here is more than 90 degrees. As long as there is one angle that's more than 90 degrees, there should only be one angle more than 90 degrees. It's an obtuse triangle. These words sound familiar? Okay, let's go to the second one. Based on its side lengths, what do we know? Equilateral. It didn't give me the tick marks, but what do you notice about all the lengths of all of these sides? They're all equal, they're all 18, so I could put the tick marks there since they're all equal to each other. This one's going to be called equilateral. So lateral is talking about the side lengths. If you play sports and you've ever talked about a lateral, you're talking about throwing the ball sideways. Sides of a triangle, lateral. For angles, how would we classify these angles? Is it a right triangle? No. Is it obtuse? Is it acute? It is acute, but even better than that, they're all the same length or same angle, so we're going to call that equiangular. They are still all acute, yes, but specifically is the equiangular one. Number 3, if we were doing it by sides, how would we classify this triangle? Did somebody say ice cream cone? Yeah, sort of like an ice cream cone, but that word is isosceles, because 2 of the side lengths are the same. If we're going to classify it by angles, what would we call this one? A right. Yeah, we see that right angle indicated by the box in the corner, so it is an isosceles right triangle. So when we classify these angles, we're able to give it 2 adjectives, something to do with the side lengths, something to do with the angles. But of course, we can make it harder than just looking at it and classifying. We can put it on a coordinate grid and ask you to do some crazy amount of work. So in question number 4, and it's almost completely worked out for you, so I wanted you to have a nice clean example. Mine is super color coded, so if you would like to color code along with me, here's what we're going to do. I'm going to use 3 colors. I'm going to use red and blue and green. The red is going to be the short side from O to P. Notice when they found the distance of the side length, they used this distance formula. We've been doing distance formula for a minute. It's on your formula chart. We plug in the x1 and y1 from the coordinate points, and we get square root of 5, or approximately 2.2. Then they come in here and they're going to do O to Q. O to Q is this side length that goes like this. So the length from O to Q, again, using the distance formula, which you can see there, another example we've done before. Plug in all the x1s and y1s, x2s and y2s, we get 6.7. Then they come over here and they do from P to Q. And again, using the distance formula, they get 7.1. Based on those numbers that they got from the distance formula, are any of the sides congruent? Wait, are any of the sides congruent? No, because they're all different numbers. So since no sides are congruent, what's the word we're going to use to talk about the side lengths? Ooh, when none of them are the same, it's scalene. Isosceles is the ice cream cone one where 2 of them are the same. So we know one of the adjectives. We found this adjective by looking at the side lengths using the distance formula. Next, we're going to check for right angles because we need to look and see what the angles are like. It doesn't look like an obtuse. We're not quite sure if it's right because we can't tell. What we're going to do is look at the slopes. So if I look at the slope of OP, again, that's my red side length. I use the slope formula, y2 minus y1 over x2 minus x1, and I simplify. We've been doing slopes for a while, and I would get -2. Then I found the slope of OQ, y2 minus y1 over x2 minus x1, and I got 1/2. I found the slope of the green part from P to Q. Using those x1 and y1, x2 and y2, I get 1/7. We're not looking for numbers to be the same here. That would be parallel lines. Lines meet at right angles when they're perpendicular. How are slopes related if the lines are perpendicular? Two words. One starts with an O, one starts with an R. Yeah, opposite reciprocals. Okay, let's look at any of our numbers here. Are any of these 3 numbers opposite reciprocals of each other? Maybe if I wrote it like this, you'd see it. What if I did this as -2/1? Are any of those numbers opposite reciprocals? The slope of the red part, OP, and the slope of the blue part are opposite reciprocals. Because they're opposite reciprocals, we know that these 2 lines are perpendicular to each other, And when they meet at a perpendicular angle, or when two lines are perpendicular, the angle where they meet is a right angle. So the two words we get to use to describe this are scalene and right. So triangle OPQ is a scalene right triangle. We had to find those two words by figuring out the distances of the side length and the slopes of the line to decide if any of them met at that nice right angle. If none of them were at a nice right angle, we'd look at the image to decide if it was obtuse or if it was acute. Now don't flip your paper over just yet. I did pretty much this entire problem and almost didn't have you write down anything. So we do need to do a practice problem like this to make sure we understand how to use the distance formula and how to use slope appropriately. So I'm going to hand your group, so each group's going to do one piece of paper that you're going to work through one problem exactly like this. You can look at the steps on your notes to see exactly what to do, but I want you to work it out with your team and see if you can get it. We're going to take about 10 minutes to see if we can answer this question, okay? For those of you needing a place to start on this, because I'm seeing a few people just not quite getting started, I'm going to use this red side length first. And I'm going to label this as x1, y1. Oops, that's a whole 2. And then x2, y2, which will give me the things to plug into the distance formula to find that distance of CA. I'm going to leave you here to keep working. I think most of us were on the right track. Maybe just need to remember to label your points. I'm going to start working a few of the parts just so you can see. But I'm not going to say anything. I'm just going to start working them. Okay, hopefully these are close to the numbers you got. How close were we to getting these numbers on all of our side lengths? I might have cut you off too soon, but were we headed the right direction? If we get these side lengths after doing the distance formula, what is our conclusion? Are any of these side lengths congruent? No. So what's the word we use to classify this by sides? Scalene. Now, Neonte had a really great point. He said, well, this looks like a right angle. I agree, it kind of looks like a right angle, but we can't trust our eyeballs anymore. We said that when we studied parallel and perpendicular lines. We have to go in, we actually have to check to make sure that that angle right there meets at a right angle. So let's find the slopes of the red and the slope of the green just to check and see if it's actually a right angle. So if I find the slope of CA, so that's the slope of the red, I'm going to use the slope formula, and I know we already have x1s and y1s listed there, but if we just, I'm going to erase a whole bunch of stuff if that's okay with everybody, so that we have one thing listed as my, oops, guess we're undoing all of that. Beep, beep, beep. So to find this slope, I'm going to use this as x1, x1, y1, and this is x2, y2. And if I use my slope formula, it is y2 minus y1 over x2 minus x1. Well, that top becomes 4 and the bottom is -1, which means the slope is -4. That means if that green line has a slope of positive 1/4, the opposite reciprocal, then they're perpendicular to each other, and so it's a right angle. Well, let's hope that's right. If I label these as x2, y2, and these are going to still be my x1, y1, the slope for BC would be 1 minus -1 over, can't reach it anymore, 7 minus 1. Well, that's 2 over 6. That is the fraction 1/3. Are these two things opposite reciprocals? No. They have to be the same number flipped over. Thank you for trying. So that means that these two side lengths, the angles of these two side lengths are not related. This would be a neither parallel nor perpendicular. That means that this angle is an acute angle, actually. So the words we would use to describe this triangle would be a scalene acute triangle. The point I'm trying to make here with this problem, and again, you have a fully worked out one on your notes so you can look back and refer to it, is you can't trust your eyeballs. Whenever it's on a coordinate grid and the numbers for the angles are not given to you, it might look like a right angle, but was it a right angle? No, we actually have to count the slopes. Now, yes, if it's on a coordinate grid, you could count rise and run to check the slopes. That might be faster for you, but some of us aren't the strongest at rising and running. We're better at using the slope formula, so that's what we're going to practice. Okay, let's move on. If you and your team didn't get it all the way filled out, I do expect that to be turned in before we leave, but I will get this put up again later when we get into our practice time, so I'll come back to this slide. Let's go into our notes a little bit. We got to talk about some relationships between the interior and exterior angles for our triangles. Now, some of this is going to be like, duh. Interior angles are angles inside a polygon, like interior angles in our parallel lines were inside the parallel line, so interior angles are on the inside. What should all of the angles in a triangle add up to? 180. This is called our interior angle sum theorem, or our triangle sum theorem. Interior angles should add up to 180, which means we can constantly set up this formula. Measure of one angle plus measure of another angle plus measure of the third angle is equal to 180. This is because if you took those angles apart and put them in a straight line, they actually would form a straight angle, 180 degrees. So if we're trying to solve for this triangle, we're going to start trying to put all the pieces together for different triangles. We know that all three of these angles have to add up to how much? 180. So my formula that I can put together would be the question mark angle plus 80 degrees plus 39 degrees would be equal to 180 degrees. At this point, I've set up an equation, and yes, it's really simple to solve. How do I get that question mark, or the x, by itself?
You can add 80 plus 39.
Yeah, I can add 80 plus 39. That would give me 119, and then what can I do?
180 minus 119.
180 minus 119, that's going to be 61. So my question mark angle here is 61 degrees. Now you might be thinking to yourself, Miss Quigley, you wrote a whole equation just to subtract two numbers from 180 to figure out what's missing? Yeah, I did. If you see it as 180 minus 80 minus 39, you would get 61. But because some of the other problems are going to require us to write an equation and solve, I wanted to get you used to seeing the equation. But again, every single time, what do those angles add up to? 180. Okay, and I know it's a little bit more, but let's look at number 6. We're trying to find this missing angle right here. Its particular triangle, this guy right here, I only have one angle written. What is it telling me about this angle, though, based on the arc mark? Where else do you see this arc mark? On the opposite side. Oh, it's vertical angle. What do we know about vertical angles? What do we know about vertical angles? Rip. When we learned about vertical angles in a parallel line, we learned that vertical angles, they're congruent. That's why they have the same arc mark. That was my yellow vocabulary word from last unit. Vertical angles are congruent. So I'm saying to you, if we figure out what this angle measurement is in the top triangle, we would automatically know what this angle measurement is in the bottom triangle, which gets us closer to figuring out this side length. So let's figure out this guy. I'm going to put my little question mark, or actually I'm going to put an X right here just so I use a different indicator. We're going to figure out what X is equal to. In that top triangle, I know that X plus 30 plus 40 is going to be equal to how much? 180, because they make a triangle. That's the point of today, that those interior angles add up to 180. So just like Kate said a second ago, what can I do to figure out what that X angle is worth? Add those two numbers and then subtract it from 180. 180 minus 70 is 110. So that means that that vertical angle X is equal to 110 degrees. If this is 110 degrees, how much is this one? Also 110. I like writing my numbers in 110, and then I'm going to erase this X and put 110 right there just so that I see in the image itself what each angle measurement is worth. Let me get my degree sign to look right. Okay, now in my second triangle, in the bottom triangle here, we now have two of the three angles. So we can say the question mark angle plus this 110 I just found plus 25 is going to be equal to how much? 180. Now again, it feels like we're doing too much because you could just subtract those numbers from 180, but stick with me because eventually you're going to have to write an equation for this. That means that the question mark plus 135, I added those numbers together, would be equal to 180. How do I solve for that question mark again? 180 minus 135, meaning my question mark angle, the one we want to know about, is 45 degrees. Does that make sense? So we're using the idea of triangles adding up to 180 to maybe solve larger problems. And yes, it is just subtracting the angles you do know from 180. But this next example is going to show you why I want you to write an equation each time when we're doing this. I know I kind of spilled over onto this problem, but for number 7, we are looking for this angle right here, and I know it looks kind of funky. We're trying to figure out what this angle is worth. But uh-oh, it's going to be a whole algebra problem because that angle is 67 plus x. Don't worry though. What should all three of these angles add up to? 180. So here we go. We're going to write our equation. We're going to say that first angle at the top, 75, plus the angle at the bottom left, which is x plus 52, plus the angle at the bottom right, which I care about, 67 plus x. If I add all of those up, what is it going to be equal to? 180. Now is when it becomes helpful to know that this creates an equation as opposed to just subtracting those numbers. Now this is a more complicated equation to solve because I have so many things floating around. So we're going to go back to the box method here. And we're going to solve using the box method. Now I'm going to make my box a little bit crooked, and I'm so sorry. It's just because I would run out of space otherwise. But I have my center line. And I ask myself the typical question. The first one is, how many x's are up there? How many x's? 2. How many things without x's?
4.
4. Very good, Jordan. 4 things without x's. So I make 4 top boxes. Now from here, again, it's just the solving using the box method, or you could use inverse operations if you wanted to. We drag and drop, we draw our arrows. We drag and drop, we draw our arrows. Nice. None of those change the sign, but when I take the 75 over here, oop, change the sign. Oop, change the sign. Oop, change the sign again. But then I don't change the sign. We do x plus x, which is 2x. And then we take all of those numbers, negative 75 plus negative 52 plus negative 67 plus positive 180. Boop, boop, boop. That's a calculator question. You type all that in your calculator. When you add them all up, you get negative 14. What's the last step to solve for x? Divide by 2. Negative 14 divided by 2, if you trust me, is negative 7. And huzzah, we found x. Was that the question? No, remember, we want that angle that I've highlighted We want to know what that angle is. Going back to when we did like segments forever ago, what can I do now with this number -7? I'm going to highlight it in red. Yeah, we can plug it in right there to x. So we can say, all right, this angle here is going to be 67 plus that -7 we just got from the problem. 67 plus -7 is going to be 60, so that question mark angle is 60 degrees. Again, this last problem is our goal kind of problem, to not allow ourselves to get confused when there's algebra involved. The first two examples were really simple, and I'm sure you just wanted to subtract those numbers from 180. Amazing. But when we get to more complicated questions, I do want you to be able to write the equations. So for me, when you're solving these on paper, I want to see the equation each time, and then you can solve it by subtracting or solve it using the box method. Any questions before we flip the page? I feel like you had a question.
You subtract this. This would be 72.
You're right. If we were trying to find this angle as well, which the question didn't ask for, you would substitute it in here.
The question they asked us what this angle was.
Correct. The question itself was find the question mark angle, which is this guy. If it said find all the angles, you'd be like, well, the top 175, this one we just found to be 60, and then you'd plug -7 in again here to get, what is that, 45. So you could find all three.
Yeah, but when I put it in, it came out to 187.
When you plugged in,
You don't do 52 plus 60 plus 75.
oh, but this one's not 52. This is x plus 52. So this would actually be, if we were, zoom in. If we were solving this, we'd have to plug that -7 right here. So it would be -7 plus 52. This ends up being 45. So 45 plus 75 plus 60 would get you 180. That's a great question. Yeah, if you ever add up your angles for your triangle and it's more than 180, something's wrong. Great question and great notice. Okay, on the last page for today, and I know they were longer notes than normal, but I wanted to give you plenty of space to actually write down the equations. Put your phone away, thank you. We have now talked about interior angles, so we can't leave out our exterior angles. For exterior angles, we're talking about the angles on the outside of a triangle, on the outside of a polygon. The sum of all exterior angles of a triangle or a polygon is going to be 360 degrees. But the main theorem I want us to practice with today is called the exterior angle theorem. Your exterior angle theorem is also called your alley-oop theorem. Those of you who play sports, you know what an alley-oop is, right? It's where you toss the ball up and then dunk it. We're going to do the same thing with this theorem. This theorem states that the exterior angle is equal to the sum of the two non-adjacent opposite interior angles. That's a lot of words. Watch it in practice. You're going to take these two angles. You're going to add them together, and then you're going to dunk it over here with an alley-oop. That's going to be the measurement of that exterior angle. So you take the angle it's not touching, it's not touching, add them together and dunk it on the outside. That's going to be how you figure out the amount of angle degrees is in that exterior angle. That's what this formula right here is telling me, but it's kind of confusing unless you think about it like a dunk. So in problem number 8, we want to find angle 1, which is this exterior angle. To find the exterior angle, I look across the triangle from it and hope I know these two angles. I know these two angles, so I'm going to add them together and I'm going to dunk them outside, which means that angle 1 that we care about is going to be equal to 53 plus 53, because we took the two opposite ones and dunked it on the outside. That means angle 1 is going to be equal to 106 degrees, which is exactly what this question was asking for. Okay, so we take the two that are opposite in it in the triangle, add them together, and dunk it. Sound good? If I was looking at number 9, I'm wanting to figure out this angle, but I only know the measurement of this exterior angle and this angle right here. How much is this angle, by the way? 90. Let's write that in, because I know it's obvious since that little box is there, but it's nice to see numbers. So we've got a 150 on the outside, we've got a 90 and then a question mark. How are these two angles related to this one? I'm going to do what with them? Add them. So if I wrote down my equation would say I'm going to take the question mark plus the 90, and it's going to be equal to 150. Let me use a different color here. Because the sum of the non-adjacent interior angles adds up to the exterior. It's still an alley-oop. Okay, how do I figure out what that question mark is worth? 150 minus 90. So if you do 150 minus 90, you'd get that the question mark is worth 60. So the measurement of angle STU, where that question mark is, STU, is 60 degrees. It's an alley-oop. You dunk it. Now again, kind of like the interior angles, those are really simple, and it feels like almost too much work to write down a whole equation because you're just subtracting or adding numbers together. But I could make it more complicated and ask you a question like number 10. Number 10 says to find the measurement of JKM. That's here, JKM. I would highlight that angle for yourself because sometimes it's confusing to remember what the actual question is here. So we need to figure out what this angle measurement is. The problem is this angle measurement has to do with x, so I first need to figure out what x is equal to so I can plug it in. The other pieces of information I have are this. How do they relate to this exterior angle? Equal when I do what with them? Yes. No. What have I put in the middle of all of these circles the whole time? In blue. A plus sign. Yeah, I need to add them together. Their sum, their adding, creates that exterior angle. So if I wrote down that equation, I would say, all right, bet, so this 70 plus the x is going to be equal to 2x minus 5 because that's the exterior angle. That's the same theorem I just used, but this time it doesn't make something that's super simple for me to just subtract numbers. We're going to create another box and solve using the box method. So I set up my line. This one's nice and pretty. I don't have to like make it crooked at all. And we ask ourselves our questions. First box, how many x's? 2. How many non-x's? 2. We drag and drop. 70 is going to go all the way over there and become negative 70 because it crossed the line, change the sign. X, drop down. That's fine. 2x, oop, cross the line, change the sign. And this negative 5, no change. Are we all following? What do I do to make the bottom boxes again? Got to add them. So 1x plus negative 2x is negative 1x. And negative 70 plus negative 5 is negative 75. Last step, Marissa, what do I do on the last part? Divide by negative 1. Very good. So we divide by the number in front of x. Negative 75 divided by negative 1 is positive 75. Now, is that the answer? Ooh, very good. Remember, that was just us finding x. What are we going to do with this x value, though? Plug it in. We care about this angle that I've highlighted in black, but we needed to find x to be able to figure that out. So if I plug that in, it's going to be 2 times x, which is 75, minus 5. Beep, 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 bop. You type that in a calculator. 2 times 75 is 150. 150 minus 5 means that that angle is 145 degrees. We're going to continually add theorems that allow us to relate different angles to different parts of triangles over and over again to then prove or solve an entire triangle. For example, we can go down to number 10 and work really hard to figure out all of the angles in this picture. One thing I want to point out to you is that interior and exterior angles could create linear pairs. Remember, linear pairs was our pink vocabulary word from last unit that said that the two things are supplementary or they add up to 180. We're talking about angles that are on the same line, that are adjacent to each other, one inside, one outside. They make a straight line, so they're a linear pair. Okay, using all the info we have from our last unit and from things we learned today, we're going to try to figure out all of the measurements of the different angles in this image. Is there anything that sticks out to you right away that you'd be able to tell me about a side length? Maybe not in number order. There's a right angle. Okay, so Kate sees this. It's a right angle. What else does that tell us? Here, we'll draw it in because that's actually great. We'll draw in the square right here. If this is a right angle, what is this one? Number 4. Also a right angle because they're vertical to each other. So what's the measurement of angle 4? 90 degrees. So I'm going to put a 90 degrees right here on measurement of angle 4. And I'm going to put a note to myself that we knew this was because of vertical angles. That was my yellow vocabulary from last unit. Okay, and then I'm going to add it into my picture because, again, I like to add my numbers as I go just to make sure I recognize each part. Okay, what else jumps out at you? Because you may see things in a different order than I do, so I want to hear from you. The 68 degrees. Okay, what does this 68 degrees tell me? Angle 2 is also 68, again, because of vertical angles. So those that are across each other like that, they're going to be the same measurement. So this angle 2 is also 68 degrees, and that's because it's vertical angles. It's vertical to that 68. Say again? No, it should be 68.
No, the bottom.
The bottom one.
To your left.
To my left.
The vertical.
This?
No,
This?
no,
This one?
This side.
This one.
No,
This one. Oh, no, that one's, it says 90.
Okay.
Is that what you're trying to see?
Yeah.
Okay, yeah, sorry.
It looked like a 40.
It did kind of look like a 40. It's a 90. Okay. My question for you now is, since we're emphasizing this 90 degrees, what's happening here between 3 and 4? What are they making? A linear pair, which means they should add up to what number? 180. So what does number 3, angle 3, have to be? If they add up to 180, this one's 90, how much is this one? It's also 90. 180 minus 90, which is what we solved earlier, is finding all those different numbers, is going to be 90 degrees. So angle 3 is 90 degrees due to linear pairs. Since we're on the topic of linear pairs, is there another linear pair you can find in this image? Angle 1, very good. If you look at angle 1, it's going to be a linear pair here with angle 2. Which means, what's the measurement of angle 1?
68.
Ooh, not the same. Remember, they're supplementary, so they have to add up to 180. 180 minus 68, if you trust me, is 112 degrees. So angle 1 is going to be 112 degrees due to the linear pair. All right, bet. We have just one more thing to do here. We need angles 5 and angle 6.
We can't do the 90 plus 68 and where we get subtracted from 180.
So you're talking about all of the interior angles, right? Kate's saying, well, if all 3 of these angles have to add up to 180, I can figure out this angle right here by knowing all 3 of them have to add up to 180. So if I do angle 5 plus 90 plus 68 equal to 180, I can solve for angle 5, just like we did on the other page. That's my interior angle. This would be angle 5 plus 158, and if you solve for that, 180 minus 158 means that angle 5 is going to be 22 degrees, if you trust me on that measurement. So we'll say angle 5 is 22 degrees, and you guys saw it because of interior angle sum. We know they have to equal 180 degrees. Now, because I'm your teacher and I really want you to notice this, without using the reason of a linear pair, how can you figure out angle 6 here on the outside? Same as what? So it would be supplementary to 5, but I want us to think other than a linear pair, because yes, it would be a linear pair. But how is angle 6 related to these two angles? What have I done with all of these opposite angles with the one that's on the outside? Look at the top of this page. What did I do when I circled the stuff and then drew a line outside? I added them. This is our exterior angle theorem. Our exterior angle theorem says that that angle would be the sum of the two non-adjacent interior angles. So 90 plus 68 would be 158 degrees. Now, yes, that is exactly what you'd get if you had used the reason of linear pair. But because I wanted us to practice that one, I made us think that way. So this is the exterior angle theorem. But if you just notice that they were linear pairs, which some of us did, 180 minus 22 is 158. So you could get the same answer using a different reason, which is why triangles are cool, because however your brain works is the things you're going to see. I'll zoom in because I see your eyes trying to zoom in. Now, like I said earlier, if your team did not get that problem that we did with the triangle on the coordinate grid done, I will put the work back up because I do need that turned in today. Your independent practice when your groups is done is a Desmos slides that has opened on Google Classroom. So if your group is done, I want you to start working on that homework so that you don't have any more missing assignments from me. Please do your homework. Oh my gosh.